Hello, today we're going to be looking at an introduction to analytical mechanics. This is based on classical or Newtonian mechanics, but is applicable where the Newtonian formulae are not easy to apply. We shall be going via the Lagrangian, the principle of least action, the Euler-Lagrange equation, and the Hamiltonian. But first, let's just remind ourselves of the basic formulae associated with Newtonian mechanics. These are all in my video on classical mechanics. A level, V equals U plus AT, S equals UT plus half AT squared, V squared equals U squared plus 2AS, and then F equals MA. Kinetic energy is half mv squared, and the potential energy, well, that depends where the potential is, but for example, if you're talking about near-Earth gravitational potential energy, you would represent that as mgh, where h would be the distance above the surface of the Earth. And those, I hope, are familiar formulae associated with Newtonian mechanics. And for example, if I were to give you the situation of a ball that is thrown at an angle into the air, it describes a parabola. And if I were to tell you the initial velocity of that ball and the angle at which it was thrown, then you could tell me everything I wanted to know. Using these formulae, you would be able to tell me the total range that the ball would take. You would tell me what the total height that it managed to get above the ground. At any point I care to mention, you would be able to tell me the velocity of the ball, the kinetic energy of the ball, and the potential energy of the ball. You would be able to tell me how long it took to complete its entire journey. In fact, pretty much anything I could ask you, you could tell me simply by the application of these equations. So why do we need anything further? Well, suppose the force that is applying is not a constant force. Suppose it varies with distance, and therefore the acceleration associated with that force is changing. You would find it rather difficult to apply these equations, not impossible, but much more difficult. So we're going to develop analytical mechanics, which helps where the situation with regard to the force is more complex. And we're going to take forward just two of these formulae, this one and this one. And what we're going to say is that if F equals ma, then I hope you will agree that A is equal to F over m. That's F equals ma, just written a different way. And that means I can now write the formula V squared equals U squared plus 2AS in this way. V squared equals U squared plus 2A, which is F over m, times S. S is the distance, remember. And now if I multiply through on all sides by m over 2, I will get that mv squared over 2 equals mu squared over 2 plus 2fs, simply by multiplying through by m over 2. And now by taking the mu squared over 2 onto the other side, we get mv squared over 2 minus mu squared over 2 equals, 2fs. But mv squared over 2, or half mv squared, is of course the kinetic energy, and that's the kinetic energy associated with the final, as it were, the end point. Minus, well, half mu squared is the kinetic energy at the outset, what one might call the initial kinetic energy. And that equals, that is not 2fs. I made a mistake here, haven't I? By multiplying by 2m over 2, I should just have fs. So those 2's here were not applicable. It was right here, but I've then multiplied through by m over 2 in all equations, and therefore I lose the 2 here, and I lose the 2 here. So this simply equals fs, not 2fs. So what we're saying is that the final kinetic energy minus the initial kinetic energy is equal to the force times the distance, and that is the work done. But now comes the question, suppose this force is not constant. suppose it actually varies in accordance with the distance. If, for example, you're talking about gravitational forces, and I'm now going to use x as the distance, then the closer you get to the surface of the Earth, the more the force increases. In fact, it's a 1 over r squared force, because the force is equal to the gravitational constant times the mass of the Earth times the mass of the body that's falling towards the Earth divided by r squared. So it's a 1 over r squared term. The force is constantly changing. Therefore, the acceleration is constantly changing. Well, we're not going to just apply a simple 1 over r squared term. Let's take any situation where the force is a function of the distance. Or let's suppose it does something like this. And we're going to go from an initial position, point 1, to a final position, point 2. What is the work done? What is force times distance as far as this chart is concerned? We're interested because we want to know what force times distance is. That's the work done. It's also the final kinetic energy minus the initial kinetic energy. Well, the work done, force times distance, will simply be the area under this curve. And that is given by integrating such that the work is equal to the integral from position 1 to position 2 of the force, which itself is a function of x, times dx. So the work will equal the integral of force f dx evaluated at the final position, that is position 2, minus the integral of f dx evaluated at the initial position, position 1. Now I'm going to assign to that term the letter b final. And to this term I'm going to assign b initial. B certainly isn't anything to do with magnetic field, and as we shall see, it's simply a dummy variable that I've introduced and will not detain us long. Now, since we said that the work was the kinetic energy at the final stage minus the kinetic energy at the initial stage, and we said that that was the work done, that means the work is BF minus BI. Where, of course, these are just these integral terms evaluated at the final position, evaluated at the initial position. Now, if we rearrange this formula here, we get that KE at the final stage minus B at the final stage is equal to KE at the initial stage minus B at the initial stage. And that's not quite what I want, because I'm actually trying to go for something that is conserved. So I really want two sums that add up together. And I can achieve that very easily by just redefining let B equal minus U. And if B equals minus U, we don't yet know what U is, but hang on in there, then KE final plus U final, because B is minus U, is equal to KE initial plus B initial, because plus U initial. Let's scribble that out and write it again. U initial, because B initial is minus U initial. So if it's a minus B, it'll be a plus U. And now we've got a conservation term. The kinetic energy at the final stage plus something else at the final stage is equal to the kinetic energy at the initial stage plus something else at the initial stage. And what are those somethings else? Well, obviously, they are the potential energy. So what we're really saying is energy is conserved. Kinetic energy at the final stage plus potential energy at the final stage is equal to the kinetic energy at the initial stage plus the potential energy at the initial stage. Conservation of energy has been demonstrated. But let's just remind ourselves that we let B, which is minus U, B was the integral of f dx. which means that u is minus the integral of f dx. So let's just write that down. U is minus the integral of f dx, where f might vary as the distance x. Well, if this is the case, we can differentiate on both sides and we get that du by dx equals minus f, or if you like, f equals minus du by dx. And now we know what the force is. The force, which may vary with distance, is simply the derivative of the potential at the point that the force is applying. So if you ever need to calculate a force, if you know what the potential is at that point, then you can calculate the force simply by taking the derivative. So for example, if we took the example we used before where we said the potential energy in a near-Earth situation where the gravitational field is not changing much is mgh, where you could equally write that mgx, because h is simply a distance and x is a distance, then what we're saying is that the force is going to be minus the derivative of the potential with respect to x. So the force will equal d by dx of mgx, and that's simply mg. And so we've now derived the force. And you can do the self-same thing if you take the potential energy with the full gravitational formula, gmm over r, it usually has a minus sign in front of it, then that's u if you like, and so the force is going to be du by dx, or minus du by dx, and that's going to equal gmm over r squared. So now we've got a way of deriving force given the potential. The force is simply the derivative of the potential at that point. The example of the ball that we threw in the air, and it described a trajectory of a parabola. And I said that if I gave you the initial velocity and the angle, you could tell me everything about the passage or the trajectory of that ball. The question I want to ask is, why does the ball follow that trajectory? Why, for example, does it not simply do something like this? Or why doesn't it do something like this? What determines the actual trajectory that it will follow if you throw the ball in the air? Now, one answer you might choose to give is that it will follow the trajectory because that is what the Newton's equations that we started this video with dictate. But that's not really answering my question. I want to know something more fundamental than that. I want to know, why does nature determine that the ball follows the trajectory that it does? What is nature doing that will make it do that? And what has been found is that if you take any position on the trajectory that actually happens, and there are of course an infinite number of points on this trajectory, but if you take any point on this trajectory and calculate the kinetic energy minus the potential energy, rather curiously it's kinetic energy minus potential energy, where you might think it ought to be kinetic energy plus potential energy. But if you calculate the kinetic energy minus the potential energy at every point and then add all those up, so you want the kinetic energy minus the potential energy at every point on the trajectory and then add them all up, that is what is called the action. And the kinetic energy minus the potential energy is called the Lagrangian. And so the action is, in fact, since if you're talking about an infinite number of points on this trajectory, then actually we say that the action is equal to not the sum of all these, but of course the integral of the Lagrangian, which is the kinetic energy minus the potential energy, for the full duration of the trajectory, so over all the time of the trajectory. And that is the action. Now, you can do that for every conceivable trajectory you can think of. But what you will find is that the actual trajectory, the one that nature will select, is the one that minimises the action. It's called the principle of least action. And what that actually means is that the derivative of the action with respect to x is equal to 0, because that's the quality of a minimum. You get to a minimum when the derivative is equal to 0. That's also, incidentally, of course, the quality for a maximum, but we're now looking for a minimum. So when the action is minimised for the integral of the Lagrangian over the time of the trajectory, which is, as it were, an integral sum of these terms kinetic energy minus potential energy, when that is minimised, that will determine the actual trajectory that the ball will follow. Now, in order to calculate this, I want to take just 3 points on this trajectory. 3 adjacent points. Now, of course, they will be infinitesimally close together, but I'm going to expand them. So we're looking at 3 points on the trajectory, and let's just magnify them out a little. So here is x, that is the height above the ground of the ball, and here is time, that's time passing as the ball moves from left to right. And we are now going to reduce that trajectory of the ball to just 3 points, which will look sort of something like there, there, and there. This is point A, this is, as it were, at time B, and this is at time C. And remember, these are very, very close together. I'm going to say that the time interval between A and B is epsilon, and the time interval between B and C is epsilon. Epsilon is a very, very, very tiny amount of time. And I'm going to say that the value of x when it's at point A is xa, the value of x when we're at point B is xb, and the value of x when we're at point C is xc. And for these purposes, I'm going to regard xa and xc as fixed. This is the starting point, this is the finishing point. The question I want to ask myself is, why did the ball go through point xb en route from xa to xc? Why didn't it do something like that, or something like that, something like that? What made it go through xb? And we know the answer to that. That is when the action, which is the integral of the Lagrangian over the whole of time, is minimised. So we need to know what the action is for this very short part of the journey. Well, the action consists now of only 2 stages, because we've reduced it to you start, you go through point B, and you finish. So the integral of the Lagrangian simply now becomes the sum of the Lagrangian going from A to B plus the sum of the Lagrangian going from B to C. So it's just the sum of the Lagrangians times epsilon, which is now replacing, as it were, the dt. What is the Lagrangian dependent on? Well, the Lagrangian, remember, is kinetic energy minus potential energy. Kinetic energy is half mv squared. The half and the m are constants. The v is what changes. As the ball goes through its trajectory, its velocity is constantly changing. And so the Lagrangian is dependent on what we call x dot. Now, the reason we do that is that velocity is the rate of change of distance with time, and we use a shorthand for dx by dt. We call that x dot. Similarly, acceleration is the rate of change of velocity with time, which is also the second differential of distance with time, and that we give the shorthand x double dot. So we can say that the Lagrangian is a function of velocity because it's a function of kinetic energy, and that's x dot. And we can also say that the Lagrangian is a function of potential energy, and potential energy is a function just of distance, x. So the Lagrangian actually has 2 variables associated with it, velocity and distance. So now let's look at the action associated with this journey from A to B and from B to C. Well, the action will be the sum of the two Lagrangians. That will be the Lagrangian which goes from A to B, which will be xb, that's one of its functions. And then what about the velocity? Well, the velocity will simply be the distance divided by the time. The distance is xb minus xa, that's how far up it goes, xb minus xa, in time epsilon. So the velocity is xb minus xa divided by epsilon. That's the velocity. And that's, as it were, the Lagrangian associated with going from A to B. But we've got to add to that the Lagrangian associated with going from B to C. And that will be xc. And then the velocity, well, in exactly the same way, the velocity will be the distance travelled, which is xc minus xb, over the time it takes to do it, epsilon. So now we've got xc minus xb over epsilon. Just to recap, the Lagrangian is a function of kinetic energy minus potential energy. Kinetic energy has as its variable velocity, which we use x dot, the derivative of distance with time. The Lagrangian is also a function of potential energy, and the variable in potential energy is distance, x. So the Lagrangian has two variables, x dot, the velocity, and x, the distance. So when we look at the action associated with this simple trip from A to B and B to C, we have to add up the Lagrangian associated with the journey from A to B with the Lagrangian associated with B to C. The Lagrangian going from A to B has xb as its final point, and the velocity, which is distance divided by time, which is xb minus xa over epsilon. And the Lagrangian going from B to C has as its position xc, and the velocity is distance divided by time, which is xc minus xb, finishing point minus starting point divided by time, epsilon. Now remember that the points xa and xc are fixed because those are my starting and finishing positions. The only variable is xb, and we want to know why the ball actually went through position xb. And we're told that the reason is that if you look at dA by dxb, that will equal 0. In other words, that's the minimum or the least action. So let's now differentiate these Lagrangians with respect to xb. I'm not going to do it the pure maths way. Instead, I'm going to do it by actually exploring what is going on. First of all, we've got a Lagrangian with a variable xb. Well, that clearly will vary with xb. So that will be dl by dxb. What about this term here? What happens to this as xb changes? Well, as xb increases, so the velocity will increase because xb minus xa will get larger. If xb gets smaller, the velocity gets smaller because xb minus xa gets smaller. So this term here is essentially a derivative with respect to the velocity at point B. What about this here? The Lagrangian is dependent on point xc, but xc is fixed. So it doesn't matter how much you change anything, xc doesn't change. So that just has the xc does not vary with respect to xb. And finally here, what happens if xb varies? Well, then the velocity varies, but in the other direction. If xb increases, the velocity decreases. Because if xb increases, xc minus xb will go down. So xb increases, the velocity decreases. xp decreases, the velocity increases. So that is shown by saying it's minus dl by dv at point C. And just to complete the picture, all of that, of course, is multiplied by epsilon, although that won't matter. So we've now got to look and see what happens in the limit. What happens in the limit, particularly with this term and this term? Well, again, you can go through the maths, which is fairly complicated, but just let's think about what's really happening. As point C approaches point B, what you are actually looking at here is the rate of change of the velocity, or the rate of change of the the Lagrangian with respect to the velocity. So as we get to infinitesimally small points, as the distance, as epsilon tends to 0, dA by dxb, which we know has got to equal 0 for the minimum, is going to be equal to dl by dxb minus, and then it turns out that it's d by dt of dl divided by the velocity, or the change of velocity at b, which we can write as dx dot b, because we're using x dot to represent velocity. And if that's the case, then this term here equals 0, which means that this term must equal this term. So dl by dx, I'll forget about the b now, is equal to d by dt of dl by dx dot. And that is called the Euler-Lagrange equation. The derivative of the Lagrangian with respect to x is equal to the derivative with respect to time of the derivative of the Lagrangian with respect to x dot. The Euler-Lagrange equation. So here it is again. The derivative of the Lagrangian with respect to x is equal to the derivative with respect to time of the derivative of the Lagrangian with respect to x dot. And that looks complicated, a good deal more complicated than Newton's equations do. But let's just see what we can do with this. Remember that the Lagrangian itself is the kinetic energy minus the potential energy, which is a half mv squared, or mx dot squared, minus, well, we'll just call the potential energy v, which of course is a function of x. So let's first do this side of the equation, dl by dx. Well, there is no x term in half mv squared. There's an x dot term, but not an x term, so you get nothing from the derivative here. And this then simply becomes minus dv, which is a function of x, by dx. But you may remember that earlier on in this video I told you what minus the derivative of the potential was with respect to x. It was the force. So dl by dx is simply giving you the force. Now let's go to this side of the equation, and first we'll do dl by dx dot. We actually want the time derivative of that, but firstly we'll just do dl by dx dot. Well, there is no x dot in the potential energy, so you'll get nothing from that. This is a half mx dot squared, because the velocity is x dot. And if you take the derivative of half mx dot squared, you will get mx dot. But we want the time derivative of that. We actually want d by dt of dl by dx dot. And that, of course, will be d by dt of mx dot, and the derivative of the velocity is the acceleration, mx double dot, which is mass times acceleration. So what have we shown from the Euler-Lagrange equation? That the force is equal to the mass times the acceleration. And that is Newton's second law. So from the Euler-Lagrange equation, we can quickly get back to Newtonian mechanics. Now let's just remind ourselves of the Lagrangian. The Lagrangian is the kinetic energy minus the potential energy, which is half mx dot squared, or v squared, minus the potential energy, which again I'm going to call v of x. And what I want to know is, how does the Lagrangian vary with time? If it doesn't vary at all with time, then we can claim that the Lagrangian is conserved. In fact, it's unlikely that it won't vary with time. Kinetic energy plus potential energy is conserved, but kinetic energy minus potential energy doesn't sound as though it's going to be conserved. But it will be interesting to see how the Lagrangian varies with time. So we need to differentiate this with respect to time. Now, how do you differentiate a term like this with respect to time? Well, the Lagrangian itself is a function of x dot and x. We've already said that before. It's a function of velocity because it's got kinetic energy in it, and it's a function of distance because it's got potential energy in it. So when you are differentiating a Lagrangian, which is a function of x dot and x, with respect to time, the way you do it is you take the partial derivative, this is all to do with partial derivatives, the partial derivative of the Lagrangian with respect to the first variable, dx dot, multiplied by the way in which that variable varies with time. So it's dl, or the partial derivative of L with x dot, multiplied by the way in which x dot varies with time, and you add to that the partial derivative of the Lagrangian with respect to the second variable, dx, and you multiply that by the way in which that variable varies with time. So it's the partial derivative of the Lagrangian with respect to x dot times dx dot by dt, plus the partial derivative of the Lagrangian with dx multiplied by dx over dt. So we've now got four terms. Let's see if we can simplify them. Well, two of them I can simplify very easily. dx dot by dt is x double dot. It's an acceleration. dx by dt is velocity, x dot. What about dl by dx dot? Well, let's just remind ourselves, dl by dx dot, there's no x dot in this term here, so you get nothing from that. And the derivative of half mx dot squared with respect to x dot is of course simply mx dot. And mx dot is mass times velocity. And what is mass times velocity? Momentum, p. Finally, what is dl by dx? Well, there's no x term here, so you get nothing from that. And this just gives you minus dv by dx. And again, I set that out earlier on. What is minus the derivative of the potential? It is the force. Now, I could put the force in here, but I'm going to simplify it still further. The force is mass times acceleration. And acceleration is rate of change of velocity, v2 minus v1 over t. And that is equal to mv2 minus mv1 divided by time. But mv2 is the final momentum, mv1 is the initial momentum, and so you've got the change of momentum divided by time. That is the rate of change of momentum. And the rate of change of momentum can be given as p dot. That's essentially dp by dt. And dp by dt can be given the formula p dot. So you've essentially reduced this equation to momentum times acceleration plus the rate of change of momentum times velocity. Now I am going to assert, and then I'll demonstrate it, that this term here is one and the same as the time differential of px dot, the product of px dot. Why? Because if you want to do a time differential of a product, you simply take one term and multiply it by the differential of the other, plus the differential of the other times the other times the differential of the first. I'll say that again. You've got two terms. You take the first and multiply it by the differential of the second, plus the second multiplied by the differential of the first. So d by dt px will be the first times the differential of the second, plus the second times the differential of the first. And that, if you want to look, x dot times dp by dt is this here, and p times x double dot is this term here. Alright, so this term, d by dt of px dot, is a simple version of that there. So now we've got that the time differential of the Lagrangian is equal to the time differential of px dot, which of course is not 0. So the Lagrangian is not an invariant quantity. It is not conserved, because if it were, the variation of the Lagrangian with time would equal 0. But we can, of course, take everything to one side. So we can have dl by dt minus d by dt of px dot, and that does equal 0. And we can rewrite this as d by dt of L minus px dot. So the time derivative of a thing called the Lagrangian minus momentum times velocity is conserved, because the time derivative of this quantity here equals 0. Which means it doesn't vary with time, which means it's conserved. But what is L minus px dot? What is this term here? Well, here's the formula again, and we want to know what this thing here is called. And for classical or historical reasons, it's actually called minus h, so that h is actually px dot minus L. So it's just the other way round. And h is also conserved, because if L minus px dot is conserved, then the negative term, px dot minus L, must of course also be conserved. And this is called the Hamiltonian. But what is a Hamiltonian? Well, let's just multiply it out. What is p? Momentum. What is momentum? Mass times velocity, or mass times x dot, times x dot, minus the Lagrangian. What's the Lagrangian? That is kinetic energy minus potential energy. The kinetic energy is half mx dot squared, or half mv squared, minus the potential energy, but you've got a minus here, so that becomes plus the potential energy, which will represent as Vx. So here we've got mx dot squared minus half mx dot squared. Well, that's a half mx dot squared, that's these two, plus Vx. But hang on a minute, this is kinetic energy, and this is potential energy, and we're adding the two together. So what we've shown is that the Hamiltonian is no more, no less than the total energy, kinetic energy plus potential energy. And again we've shown that that function is conserved.